So last time we talked about trips. We finally finished with trips. What's happening? Oh. Sorry? Is it like, does it see me? Okay, now it sees me. So we started with trip and finished with the trip last time, and then we wanted to look on different trees that helped us to perform operations on segments. Today we will start another topic, which will be with us like 3 or 4 lectures, I don't know exactly right now, and it will be dynamic programming. It's a very important topic, so that's why I spend the most time on that. And we start with the simple implementation of how to calculate the Fibonacci number. So we know that fib of n is equal if n is equal to 1, then return, like n is less than or equal than 1, then return 0. Otherwise, return fib n minus 1 plus fib n minus 2. Okay, that's the simple implementation of the how to calculate Fibonacci number. So the Fibonacci number n is equal to the Fibonacci number n minus 1 plus Fibonacci number n minus 2. So what's really happening here? The dynamic programming is the way of the algorithms how to think about the states. So we have a state, some state, and we kind of build the state from the previous ones. So like, as you remember, there is an induction. I think we asked you during their exams when you got into the program. And the induction is the following. Kind of you have an induction 1, so kind of you proved everything for 1 to n minus 1, and then you make a step to n. So kind of you can calculate the answer for n given all the previous answers. So the dynamic programming is the very similar structure. So instead of 1, n minus 1 and n, we will have some state, and we can we can kind of say which state is bigger than which one. So there is a partial order on the state. So kind of this S1 is less than S2, but it is not necessary that there is a relation between them at all. And we kind of do like we go from the state to the new state. Kind of we calculate the answer for the state from the answer in the previous states. So that will be the main goal of dynamic programming, is kind of to understand what the state of the program is, what is the state, and then how to recalculate it from their previous smaller states. Okay, we started with Fibonacci number. What is the problem with currently with this solution? Do you see any problems? Like, what is the like the running time of this algorithm?
Well, it would calculate all the numbers. So
it will calculate all the numbers. Yes.
It has a linear complexity from the number itself.
Yeah, it has linear complexity of the Fibonacci number, because when you go Fibonacci n, you make 2 calls. Fibonacci. So kind of you calculate Fibonacci n from 2 Fibonacci n minus 2. Then you calculate Fibonacci n minus 2 from Fibonacci n minus 2. Fibonacci n minus 3, and Fibonacci n minus 2, we again go from Fibonacci n minus 3 and Fibonacci n minus 4 and so on until we got to their state where n is less than or equal to 1. Okay, obviously there is a problem that we calculate some of their states. So consider right now in this program the state will be n. So we know, like, from the state n, we know how to recalculate it from the previous two states. So this is this state and this state from n minus 1 and n minus 2. So this is kind of simple program. So what's happening here? You can see that we calculate the same Fibonacci number 2 times. Like, and Fibonacci n minus 3, it will be calculated like 3 times here, and so on. We want to get rid of that. This is kind of what is doing their dynamic programming with memoization. So what is the idea? So you can see that when we calculated Fibonacci n minus 2 the first time, we don't have to recalculate it the second time because we already know the answer. So how to deal with that? We will create an array answer which is filled with minus ones. And we will do the following. If ans of n is not equal to minus 1, then return ans of n. Otherwise, we say ans n equals to Fibonacci n minus 1 plus Fibonacci n minus 2, return. So what is the difference with our previous program? Is that kind of we memorize the answer for the state that we already visited. So for example, here, if we already we already recalculated the answer for n, we just simply return this answer. Otherwise, we recalculate recursively from n minus 1 and n minus 2. Okay. What will be the complexity of this program already? So the previous complexity was of fib of n, which was very long because like this grows exponentially. What will be the complexity of this algorithm?
So we would have to just calculate all the numbers, so it would be linear of the number of the Fibonacci number.
Yeah, so yeah, that's true. Then we calculate this in O of n time, because we recalculate each state only once, and that is why it is only once calculated. Okay, so we know how to deal with memoization. There will be much harder algorithms where we need to make states like kind of not the whole state space is reachable. So we go only for the states that are coming. So so it will be like program state S. If S is small, then return some answer. Answer of S. If ans of S is not equal to minus 1, return ans S, and then ans S, which will be recalc from S1, SK, like which are smaller states, and then you return S of S. So this is kind of how their memorization works. So this is exactly as you can see their induction here. So we go over previous states, and we calculate only for the states that are necessary. we do not recover non-reachable states. Plus, we have a base here, so if f is small, then we can take their base from the induction, kind of, and put it as the answer already. So for the small states, we know the answer by hand or some other way. Okay. This is about the generic approach and how to do that. We will start from the simpler approach, to be honest. So we still count in Fibonacci number the same way, but we know that all the states of the Fibonacci numbers are integer, because we only kind of our state composes from one integer, their identifier of the Fibonacci number. So let's create an array fib 0, 0, 0, and then we say at the beginning fib 0 equals to 1, fib 1 equals to 1. And then we can make exactly as induction is doing this. So we iterate over all for I from 2 to n. We do the following: fib I, what it is equal to?
I minus 1 plus I minus 2.
Yeah, fib I minus 1 plus fib I minus 2. So we are doing exactly as induction. We set the base, and then we go over the all states and calculate it from the previous states. So again, as you can see, the complexity of such an approach is already linear, so there is nothing memoization, there is no memoization, etc. So it is much cleaner and simple. Okay, let's start solving the following problem. So we have a line, and there is a grasshopper jumping. So the grasshopper is the guy who can jump on one cell and on two cells. So he's sitting here. And it can jump for 1 and can jump for 2. And the first simple question is how to calculate the number of ways the grasshopper can jump from here to this to end. So we start from cell 1, and we can do like each step we can choose 2 jumps. We can choose one, like on 1 and on 2, and we want to calculate the number of ways on what is the number of different ways to jump from the first to n.
Also, there would be cases where he'd done one, for example, all the one size jumps and one two size jump, and then there will be all the permutations where we could put this two.
Yeah, this is a little bit already complicated. Let's come up with the state of the problem. What do you think can be the state? So like this grasshopper jumped over made some jumps, and what will be the state? That's the main question for dynamic programming. What is the state?
Maybe the state could be well, it could be either his position or all the jumps he made. I don't know it. If you want to calculate.
Okay, so like one of your answers is correct. So like let us a little bit like do this. Okay, the state will be their position in there. So we know I. Okay. from where we could jump to the I.
From the n minus 1, I minus 1, and
Yeah.
I minus
So what is the number of ways to jump to the state I?
in one jump it's 2.
Kind of. So
From the beginning.
suppose we want ways, calculate ways I. Okay. So you know that you want to calculate this value from I minus 2 and I minus 1 because these are the ones from which you jumped, right? So can you tell me right now how to recalculate ways I given ways I minus 2 and ways I minus 1?
Well, it would be the sum of ways
Yeah,
to I minus
exactly,
1 and I minus 1.
exactly. It would be the sum ways I minus 1 plus ways I minus 2. You can see that this is right because you can jump like this, like the ways of how to jump to I minus 2 and doing one jump here is different from jumping to I minus 1 and jumping here. As you can see, this is the Fibonacci number already. So like that's quite simple, and you can recalculate the same manner. Okay. The next algorithm, the next question that I come up to you is, suppose now the grasshopper can jump not only by one and two jumps, but also 1, 2, 3, 4, and etc. k. So it can jump much higher right now. And we want to calculate the number. Still, there, like the question is the same. How to calculate the number of ways to come from 1 to n? So, okay, Artem is doing this in there. Artem, right? Ismagilov.
Yes.
Yeah, like he's there. Okay. So what do you think will be the state again?
It could be position again.
Yeah, it could be the position
again.
again.
Fixed?
Okay, great. So ways I, then what will be, how to calculate ways I?
It would be also to add up all numbers from.
Yeah, it would be like considering all the jumps that are coming to that state. So ways I minus 1 plus etc. plus ways I minus k. Okay. Okay, that's reasonable. So let's write the program. So we know that ways for 1 equals to 1, and then we go for I equals from 2 to n. We say for j equals to max I minus k to 2. Oh, sorry. I minus k from 1 to I minus 1. And we say that ways of I equals to ways of I plus ways of j. So we just roll over all the previous positions from where we can come up, and then we calculate exactly the from the previous k iterations. Okay, what will be the complexity of this algorithm? If k is not constant.
It would be O of n multiplied by k.
Yeah. So this is O of n multiplied by k. Okay, good. Then an interesting question. Can we optimize this to O of n? Any ideas? So kind of how to calculate this guy in O of 1. So that's the question. Like, is there any way to do that?
Well, we could store partial sums.
Mm-hmm. And what we do with that? So if we store partial sums, so we have sums I, sums I. Okay, so how to recalculate then this guy? How to
sum of I plus 1 would be equal to sum of I minus ways of the beginning. So well, we shifted the window.
Sum of I minus 1 minus sum of, let me do this, kind of like that, right? So we want to take, like, what sums I means? Sums I means take their sum of all the previous guys, and kind of the ways for I is their partial sum between I and k, I minus 1 and I minus k. So here is I, and here is I minus 1, and here is I minus k. Like we want to know the sum here. But you can see that how to calculate this given their partial sums, it's like calculation of this suffix or of this prefix minus the prefix of this. Then you can calculate. So there is a little bit cheaper way on how to do that. Can you do this a little bit simpler than maintaining their partial sums?
Well, in terms of memory, we could store just one sum, only sum, if we still have ways. So there is this black area, and each time we go to the next element, it shifts by one element.
Yeah, exactly. When you move, like we want kind of to maintain this sum, right? Then what's happening when we shift by one? We remove this,
yes,
and add this. So like this are another way, and the third way on how to calculate this, it is ways I equals to ways I minus 1. 1 minute. Yeah, ways I minus 1 minus ways I minus k minus 1 plus ways I minus 1. It's a little bit complicated here. Like
it should be sum somewhere.
No. The interesting thing that this sum here is itself. This guy is itself ways of I. It's itself ways. So kind of what you do, you like when you go to I plus 1, you want to know ways of I, and then minus the weights for this guy, because you moved to the right. You want to calculate this right now. So it's kind of weights I plus weights I minus I minus k. So that is why weights I minus 1 appears here 2 times. Yeah, it's a little bit strange, but that's kind of the problem that is a little bit strange. Okay. Okay, cool. So we know how to do with prefix sums. The next question is, please tell me what's happening if there is a special array, like block it, which has some false, true. This means that we cannot jump on the cell that is blocked. So kind of we have an array, like the if cell is blocked if blocked of I is equals to true. How should we change the algorithm? Like at first, let us consider the first algorithm, right? That works of n times k. What we should do in order to...
In the first case, we shouldn't, we should just keep the j of the block.
Yeah, if block j, then continue. Okay? There is an even better way on how to deal with this. Just not to check each time for the blocked, but just not to calculate the blocked. This will have the same effect, since their blocked position will be set to 0 automatically. If you do not calculate it, it will be set to 0, and then you can calculate like that, and then you again can calculate partial sums on that, or you can do like write in a place for the weights. Okay. Now the problem will be a little bit more complicated, so we put the coins. So this is C2, C3, CK, and etc. Cn. And now our question is not how to, like, they can be negative and positive, so kind of there can be given coins to the grasshopper, or they can be taken from the grasshopper. And the question is, please maximize the total number of coins that grasshopper will get when jumping like this ways. So the first question, if all their elements are positive, then what is...
collect all the coins?
Yeah, we can collect all the coins. Like, there is a small question whether there is a blocked path of k. Like, there can be a blocked path with the distance k. So there are two options, right? Either you get all the coins, or you don't get anything because you cannot jump to the end. Yeah, but that is why the coins can be like these numbers can be negative. So what should we do? So suppose now it's not the waste, it is cost. So what will be the cost? Like, again, yeah, the state is still the same. Kind of, we haven't changed anything in the problem. The state is still the position of the grasshopper, but the answer for the state is a little bit different. The answer right now is what is the maximum number of coins we can get by jumping into state I. Okay, so how to, like, this will be an array cost. So how to calculate how to recalculate the cost of their ith position?
I guess it should be the does the cost of the ith position include the cost of the positions?
Yes.
I guess
Yes.
it should.
Yeah. So this is exactly how many coins we can get when we jump to I.
Okay, so it should be the maximum of all the available.
Okay, so it should be like from where we can come. We can come from I minus 1, 1 minus 2, etc. and I minus k. So how to get from this answer? We just should jump from the place where we maximize the number of coins. So we get like max cost I minus 1 plus ci. Let's not forget to add the number of coins that we get to the I. Of course, if it is blocked, then we don't have to calculate anything and like kind of set up there minus infinity or something like that. Okay. Again, like how their code will be changed, it will be a little bit different. So we could say cost I equals to max cost I cost j plus ci. Okay, right? So like this, the cost for I is maximum over all the cost j's plus ci. Yeah, that's reasonable, right? So this is exactly how we recalculate. The question is, like, this approach will take n times n complexity. But can we do something similar to improve the complexity to the linear?
Well, we can once again store the maximum of such a window.
How to do that?
For the last case, if the new number is
the problem with kind of this approach that you are trying to come up is that this guy could be the maximum, and kind of if we remove it, like everything can change. But we already did this.
we could do the stack of maximums. I don't know.
Almost, but this is not the stack. What's happening during one step? So it was like that, and then what's happening? This guy leaves from the front, and this guy pushes to the back. So what this data structure is?
Would be the queue.
Yeah, it is the queue.
Maximum.
Yeah, and we already know how to deal with the queue with maximum there. Okay, we know how to do this in constant time, amortized constant time. So that is how we can get from O of n times k to O of n. Okay. I think that is it for this grasshopper. So we already know. Of course, there can be a little bit more complicated task, kind of that it can jump not by 1, 2, 3, and etc. k, but on the special jump. So kind of it can jump on J1, J2, J3, and etc. Jk. But as you can see, there will be not really so different from this, because you just have to recalculate kind of not from -1, but from this thing. Just it's remained the complexity, the problem remains the same. The only thing that you cannot do the q there, and you have to work in O of n times k. Because if the jumps are not consequent, this will be not q. This kind of some strange operation, and yeah. Okay. Now the problem will become more complicated. Again, we just go like we continue to add some constraints on the problem, and right now the constraint will be the following. So suppose the grasshopper did a jump of size j, okay? Then the grasshopper can make only 3 jumps. It can jump on j minus 1, it can jump on j, and it can jump on j plus 1. So if he jumped with 5 there, then he will jump only by 4, 5, or 6. So that is the grasshopper can increase his speed only by 1 each time. So what would you consider the state here?
It would be the current speed.
Okay, the current speed, that's good.
And the position.
And the position, great. So these are the states. This is the state. We have like their position and their jump. So can you tell me from which state we can calculate ij? What are the states from which we can get there?
It would be I minus j.
I minus j.
Well, it also could be plus 1 or minus 1. So I minus j minus 1 and I minus j plus 1.
I minus j what?
I minus, well,
this is the position.
Okay, so when
and the jump?
The jump is j.
J, okay.
The other one would be I minus j minus 1.
I minus j, I minus 1, okay. With
the speed j plus 1.
J plus 1, yeah, and finally
I minus j plus 1 and j minus 1.
Yeah. So we just want to know from which state we can come into this. We can come here from only 3 states because their previous jumps can be j plus 1, and j minus 1. So this is a little bit different rather than we told before. This is their this is not the jump from which we came, but the jump that can be the next. It's a little bit different, but I mean in general they're. So to be more precise, if we count the last jump, if we come from there, it's like, but what if we do the dynamic programming, like the state was I and the jump that we get into I.
So j is the jump
which we came here, not that is going to be, but from which we came here. So how does this change?
There will be only one.
No. It's not 1. The position will be 1. Yeah, the position will be 1, but the states will be still 3. How to change?
Okay, yes. So yes, it will be I I minus j position, but
yeah, it can be I minus j everywhere, because this was the last jump exactly with the j distance. But the previous jump from there can be of 3 types
yes.
that we can get to this. It's either j minus 1 or j plus 1. So this is about this problem. So kind of we just have to calculate only these guys. There are 2 ways how we can calculate the dynamic programming typically. There is a backwards manner and there is the frontward manner. So this guy is the backwards. So kind of we ask the previous guys, what are you doing? But there is also can be the future. So it will be I plus j with j, I plus j minus 1 with j minus 1, and I plus j plus 1 and j plus 1. So like this is in the different order, kind of from where we can jump from this state to the next one. So sometimes the dynamic programming is calculated forward, sometimes it's calculated from backwards. So there are 2 ways how to calculate it, to be honest. Okay, so this is about the grasshopper. I forgot one thing that I had to, like when you think of dynamic programming, there is also the problem not only to calculate the answer, but to get how we get to that position. Okay, for that, typically we do an array from state S equals to the state from which we came. What was the best state from which we came? So, for example, previously when we have a guy who's jumping on 1 and etc. k, we can just say we can go over maximums and take the state that was corresponding to that maximum. So here is the same going. So what will be, like we calculate the maximum of this 2, of this 3, and we want to restore how we jumped over, sorry again. Like I have forgot the following thing. Where will lie the answer on this problem?
Is this also about coins?
Yeah, like this jumping ij is also about coins. So kind of this is calculated as the maximum of this 3 plus the number of coins and I. Yeah, I forgot to ask about that also.
Well, it's the same way. We should also store the maximum.
No. The first question is how to get the answer on this problem. We haven't told about that. I haven't talked about that. So like, can you tell me? So we calculated the whole kind of table, which is n times n. Then I think it is obvious that the complexity is n squared. So we calculated kind of this square. So what will be the answer to the problem? Like the maximum number of coins that we can get by jumping in this manner. Where the answer will be. Like previously the answer was simple. It was just their answer for their nth state. Okay, but now we have kind of 2 states. We have n and the last jump. Or, yeah, the last jump that was done. So how to calculate the final answer in the problem?
Well, it should be the maximum of the last jump with all the speeds, I guess. So we did.
Can you tell again?
So
The
we
maximum of
did
what?
maximum of all the last jumps. So we could do many
Yeah.
last jumps with different speeds.
Yeah, exactly. So we have the answer will be maximum for all jumps with like dp, it will be dp, n, and I. So this will be the answer. So kind of we know that we should finish at the position n, but we don't know what was the last jump, so we should go over all the jumps and calculate it. So how to do the backward procedure here in the same manner. So we just say from ij, for example, the last jump from here, like I don't know, like j plus 1. So how to get there? We just like if we know that from ij is j plus 1, then we know that we should move to the state I minus j and j plus 1. So and by that we can restore all the cells that we visited during our jumps. Okay. Okay. Now, like, let us go a little bit further. Again, let us talk to the next problem. The problem is about turtle. So it was about grasshopper who jumped here. But now like grasshopper jumped over the line, and now the turtle will be going on the rectangle. So we have a turtle here. And there is, again, the cost in each cell, where like then either the turtle should pay or turtle, I don't know why animals has coins, but that's other question. So and the turtle can go to the right and down, and that's all that it can do. It can, like, on one step it can go right and down. And the question is, can you tell me how the turtle should go in order to increase the amount of money she can get to the lower down, like right, bottom right cell? So the simple question, first question, right? What will be the state of this problem? And what will be our target dynamic programming?
The state would be the position of the turtle.
Okay, great. So the state is the position of the turtle, ij, and what will be the dp itself? The dynamic programming, what we will calculate?
The collected money, I guess.
Yeah, the maximum collected money, right? The maximum collected money to get into this position, okay? So, okay, the question is, what are the previous states from which we can come?
The previous is either I-1 or J-1.
Yeah, so we can go on either from the up or from the left. Then we can get here from I-1j and ij-1. Okay, so how to recalculate? It's pretty simple, like dp ij equals max of dp from up maximum dp from left plus Cij, and that's it. That's how you just calculate. That's exactly this thing, but exactly the thing with the grasshopper, but our state is a little bit different. So of course it can be a little bit more improved. There are several other ways on how to deal with that. Okay. Let's consider the following problem. So like luckily right now we have a simple problem so that the state are obvious in the sense, so we can see on the problem and understand the state where we're going. So you will be in your homework, there will be a problem where there is a very strange, like, this is their field and there is a chess figure knight is standing in 0, for example. Then we want to calculate how many ways there exists to get from 0 to, I don't know, like it is like their like from the phone pad. I'm pretty sure you know that. So sorry, it should be. Haven't used a button phone for a while. Already forgot how it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. For example, we are standing on 1 and our question is how many ways the knight can jump to get to their position 6. I don't know, like doing I turns. Okay, and turns. So we want to go from 1 to k and doing and jumps by the knight. For example, the knight from 1 it can go to 8 and to 6, like 2 times down and 1 right, and 2 right and down. So what will be the state of the dynamic programming here?
The position again.
The position.
And the number of turns maybe?
Yeah, and the number of turns, exactly.
I missed what do we need to calculate? The number of turns?
The number of ways, to jump from there 1 to k given by doing n turns. Mm-hmm. Yeah, so exactly. Their state here is pretty straightforward. We just calculate the number of turns that we've done and to the place where we stops. Okay, the question, a little question. So we will spend n times 9 memory on that. Can we reduce the number of memory to O of n? Oh, sorry. The number is 2 of, like, this is constant. I'm just giving it. So if you store this dp with all the turns, then your total memory will be O of n, because for each number of turns you store the whole the answer for the whole table. The question is how to reduce their memory from O of n to O of 1. Okay, let me give a little bit of hint here. So we have from where we can go to nk, right? We can go from n minus 1 k1, n minus 1 k2, etc., n minus 1 kt. What is common on all these states?
N minus 1.
Yeah, n minus 1. So we kind of, the number of turns is growing step by step. So we cannot get to the turn n from turn n minus 2. So we don't have to store it at all. So let us store only their their dp for the dp I minus 1, and we recalculate from it dp I. So with memoization, this will not work, for example, because we will go recursively here, etc., until we kind of explore all the possible states from which we get here. But here we can get from, if we work in the normal manner, we can see that from the I minus 1, and only from I minus 1, we get to I. So if we know the dp for I minus 1, then we can calculate the dpi, and then we can forget about this array. We never will get from it anywhere. So of course, if you want to calculate, for example, their way on how you get to the position, you cannot get rid of it. You have to have from somewhere. But in this case, when you don't have to calculate their path itself, but only have to calculate the number of ways, then you're fine with that. Oh, Artem had another. He had position and the number of jumps left. Yeah, that's true. Like, that's almost the same as, like, there will be, instead of n, there will be like the n minus this number. Okay. Great. So you understood the basics of dynamic programming. Let's deal with the following problem and we will stop for today. So the problem is longest increasing subsequence. So what the problem is? The problem is that we are given an array A1, A2, AN, and we want to find some A1 so that this holds with the longest k. So we have to find increasing subsequences that are increasing from left to the right, and we have to find the longest one from it. For example, 1, 3, 2, 5, 4. It will have the longest increasing subsequence as 3. So like 1, 2, 5, or 1, 2, 4, or 1, 3, 5, 1, 3, 4. So they're on like, but the answer is only 3. We cannot go longer. So let us think a little bit. What can be the state of this problem? That's So the question is a little bit more complicated. So there is, there will be, you have to come up with the state and their answer for the dynamic programming. What the dynamic program will store itself. So that it's a little bit complicated. The last number plus length. Artem, can you give me what means the last number? And what means the length? So can you write the states? The state. The last number in sequence and the length. Like let me check. So last number in sequence and length. So this is the state. Last number and length. Okay, how to make what is the kind of the steps? What is the recurrence here? What are the previous states from which we can calculate this? Yeah, and can you tell me what is this? So what is this dp is? What we store there? Yeah, Artem is a little bit confused, but I mean, the idea is close. So there is the last number and the length. But it's a little bit different. Like this is not the state. Yeah. But you don't use position array. Yeah, that's true. But you have like this last number. Which is kind of similar to the position array, right? So did you come up with something?
Well, maybe we could have just the position in array as a state.
Okay, yes.
The length of
the position in array.
The maximum length of sequence which ends in this number.
Mm-hmm.
This position would be our optimizing metric. And the previous state would be the previous number.
Okay, so we can come from this position to another position. You mean that, right? Like this. Okay, so you have the dynamic programming, which by position gives you the longest increase in subsequence that ends at this position.
Yes.
Okay? What other steps of the dynamic programming? How to recalculate it? Like, see, that's right. That's the dynamic programming that we are targeting to.
Well,
But the question is how to recalculate.
so if you go in forward, we probably should take the minimum number which is larger than the current number, and that would be the next position, and the length would just be increased by 1 in that.
You just want to take the closest one.
Yes.
The closest one. So, like this position, do you want to take the closest one? Unfortunately, this, like for example, like that. I don't know. So for 2, you know the answer is 2. Then you take the closest, which is closer, and the closest is this one. But as you can see that the maximal longest increase in subsequence is 1, 2, 4, 5. So we cannot do only the closest one.
Well, actually, I was talking about the smallest, but there's the same problem.
Yeah, so it's a little bit complicated. It's almost as you said, but like you need to tweak a little bit. Like let's get from the following. So again, let's make their backwards dynamic. So we want to calculate the dynamic program for this position. Okay, so we kind of should, from which position we should count? We can count, I don't know, from position 1, from position 2, from position k.
Well, from
the question, from which position we can move to this dynamic program?
From every position which is smaller than this number.
Yes. So for every position for which a pos I less than a of pos. Okay. So we can go from any, like kind of we make a jump from step from any position where the lowest, like the number which is lower than ours currently. And what we should do out of them. So we know right now we know from which states we can jump there. We can count. But what is how to recalculate right now?
We should take the maximum metric, which is length. So
yeah, we should take the maximum of this dp's.
Yes.
And increase by 1. Yeah, that is how you get the longest increase in subsequence. What is the complexity?
Well, I guess it would be.
So yeah, Artyom was almost also right with the program. But like what? Let's understand what is the complexity of this approach.
Well, we should go over all the numbers, so it will be n multiplied by the cost of calculating the maximum, I guess, of the subarray before, of the prefix.
No, not a prefix, because you have this strange condition that you can only jump from a pos I, which is less than a pos. But like, I mean, let's start from the simple solution. We will improve it. What is the complexity of the simple solution? Very simple. You just take the position, go over all the guys here, check this condition, and update their dp pos.
It would be squared.
Yeah, it will be squared. Okay, great. That would be squared. Okay, but now we will use what we learned previously. So, we will try to make out of n squared of n logarithm n. Which data structure gives us such a logarithm n?
Well, it would be all the trees.
Yeah, binary search tree gives us. So we have somewhere binary search tree somewhere. We don't know yet.
But we should also build it.
Yeah, of course. We should also build it. But we build it from left to right. So that's their main inequality here. That we only go over all their elements that are smaller than us. So can you come up from this suggestion, their algorithm?
Well, if we have a binary search tree, we should just find our element in it.
What you can find?
We should find our element in this tree and take well, the left branch. That would be the smaller element.
Yeah, okay, then what do we store in this tree?
The numbers themselves. Well,
You want to store like a pos in the tree. And that's it. That's it that we want to store there. You want to calculate the answer for the problem, so you have to store something, also something.
well, yes, the number could be this key, and the value stored would be
Yeah,
the
and
length.
dp of pos
Yes.
in that. Okay. So how then to so suppose we go from left to the right and come to the position and we know that the tree stores all the positions for pos less than pos. Okay, so the question, how we could calculate the answer for the position pos. So we know that the tree contains like these ones, these guys.
Well, we should insert this our new element to the tree. Oh, but we don't.
Yeah, we don't know it yet. How to get it from this tree. So suppose that we have a trip, right? So with trip it will be a little bit easier. So again we have a trip, and what we want to do. So like you have a tree, and yeah, and what we're doing. Here we have insert, and we have insertion, deletion, we have split, we have merge.
Well, we could split by our key, our new key.
Okay, we could split by a pos. Okay, then we will have two trees. We have like everything that is less than a pos and everything which is higher than a pos. And what we're doing then?
We should take the maximum value of dp from the left tree. And did we make a tree which has priorities of dp, or is it a classic?
No, we have priorities is random. This kind of the key.
Okay.
This is the key. They're the last element, and it's dp. What can we do on the tree? We did this several times. Okay, let me say, I'm pretty sure that you understand it. So, like, you can calculate the maximum on the whole subtree given some keys. So we can given the keys, we can calculate some value on the subtree and let it be the maximum over dynamic programmings from of the second values. So instead, like previously we already talked, like for example, we can increase like by x and calculate the sum on the subtree. Like this will be a little bit different. We will calculate the maximum in the subtree, but given that the value itself is the second one in the key.
Okay, so it's stored also in the nodes.
Yeah, we store this pair in.
I mean the maximum, but.
Yeah. So the it is exactly the same as we talked like with when we calculated the sum, like how we calculated the sum in the subtree. This is exactly the same. Instead of sum, we just have maximum, and then we make like we make this recalculation, like function recalc on the trip that will recalculate their maximum of the two subtrees. Okay, given this, you just can calculate the maximum out of everything that is less, and then we just calculate the dp in n logarithmic n time, because like each time you add a new node, each time you split only once and get the answer on that. So like we iterate n times and get logarithm n complexity for each step. Okay, I think I will stop here for today. Any questions?
Will it be also amortized complexity because of the
No, it will be not amortized. That's a little bit different. We have amortized and expected time. Like amortized time is that we take the whole time and split into kind of in chunks. And this is kind of amortized time. I mean, in summary, it will be, in sum, it will be some fixed amount. Expected means that it is randomized. So you don't know, like kind of you know that on average, each operation will be counted in logarithmic n time on trip, on average. We don't know that each time. It can probably logarithm n, it can be even square root of n, I don't know. But on average, it will be logarithm n. Like the expectancy is like, did you have probability theory?
Yes.
Yeah, so you know the expected number of some random variable is some average of this. So this is exactly the same here. Like this logarithm n is the expected time that we spend on our operation. Of course, you can do the same with AVL tree, but it's simply more complicated rather than with the tree. But the complexity is kind of the same. It is still logarithmic. Also, you can do the same with the segment tree, like that we discussed last time, is that the segment tree is the guy like this, which is built on array and looks like heap. For that, we can sort all the elements here. With let us make a pre-calculations. So kind of we sort all the elements and we set for each element one value from 1 to n. So you sort these guys in sort, and you will get like a prime 1, a 2 prime, etc., a n prime, and then we want to replace each a with the number in this array, in the sorted array. So kind of we replace each random number with some number from 1 to n. It will not affect the longest increasing subsequence at all, but it's just the renormalization of the values. So like you sort and then you do binary search. You take A1, find the binary search where it is, and write this index here, and etc. Does it make sense?
Yes.
Okay, and then in this subtree you just go from left to right and write at there. If you have value x, then you write here dp of x. Oh, sorry, a of x. You write dp of x, and then when you want to know their on the prefix, you just ask this tree for the prefix, and it will do you the same thing with the proper logarithmic unbound, without expectation.
Mm-hmm. But we do the pre-computation.
Yeah, but we have to done some pre-computation because like that you can index each value by like from 1 to n. Because this is data structure is not dynamic itself. In the trip you can add a new node with any key you want. However, the key is always some integer from 1 to n. That is because you just map at first all these values to the integers from 1 to n, and then you do on the string. Okay. Any questions? Additional questions? No? Okay, then we will finish for today. Thank you very much for coming.